Understanding the linked list, what it's good at, and its most important algorithms is pretty important in CS, and it's what we'll cover in this video. If you're new to data structures, check out my video that gives a high-level overview of most of them and then come back. Also, this is going to be a series, so it might be better to do these in order. Good news though, this is the first one. Okay, what is the linked list? Check out this node. Put a bunch of these together and they form a chain, which becomes our list. But let's just look at one to get started. The node can hold a piece of data like a number, which is normally stored in the .value property. Our node is just floating in space, so it's not very useful. A pointer will have to connect us to the next node in the list. The end of our list doesn't point to anything. We can access this pointer through the .next property, and we could also set it to point to a new node. Now when we form a chain, you can see why it's called the linked list. The first node's the head, then you can follow the pointers or traverse the list until we reach the end, which has a null pointer. This is the tail. In code, there's different ways to create the node. To explain that, we need a quick tangent first where we define a few terms. Usually I try to avoid jargon, but two terms are really important, and that is interface and implementation. When we talk about a data structure or an object's interface, that defines how we interact with it. We do this through properties and methods. We already talked about two properties, .next and .value. They just give us info that's stored on our node. Methods, on the other hand, can perform actions on the node, changing this info or doing different things to our list. In other words, they're functions stored on an object. An example of a method would be adding a new node to the end of the list or retrieving the value at index 3. Now, what's implementation? It's how we actually code our data structures and our methods. You can write the same method 100 different ways with terrible spaghetti code that's really slow, or the most beautiful code you've beheld in your life, and luckily you can't finish too fast in programming. The important thing is that they work though. The interface doesn't care how methods are coded under the hood. Just like someone who's viewing your website doesn't care how the code looks. In any case, now we can talk about the implementation and interfaces of a linked list. Let's implement a node as a class. You have classes in every language that supports object-oriented programming. JavaScript and Python are the two I like most, but classes always have a few things in common. Think of a class as a factory that creates objects. So with one node class, I can create as many nodes as I want. Classes always have an init or constructor function, which tells the class how to set things up. There also needs to be a way for the object to reference itself, which we'll use the self or the this keyword to do. To tie this all together, if we want to create a node with value 4, we have to set self.value to 4. We'll also set next to none, meaning this is the tail of a list.
Let's think of methods we'll definitely need in our interface to do different things to our list, namely add to tail, get from an index in our list, and to delete a value from the list. Let's start off with the add to tail method. We'll initialize our list with a new node. This part's really important. We can move throughout our list by storing a pointer to the variable on, keeping track of our current position. Here we want to move on forward until we find the end of our list. We do this by setting on to on.next until we find the end of the list, or null. When we hit null, we'll know to create a new node with the value that was passed in. Finally, we'll set on.next to that new node. In this example, where the list is already size 2, you can see on moving forward, and then the implied on.next moving with it. Finally, when we hit null, we'll add a new third node with value 3. Finally, let's write some code. I'm just going to write Python code since the JavaScript is pretty much the same. Let's create that add to tail method on our node class. We'll of course need value as an argument. Remember, in almost all these methods, we're going to need the on pointer to traverse our list, so let's write that first. Since we're writing a loop, we have to think of our break condition, which will be when we hit the end of our list, or on.next is none. Finally, in the body of the loop, we'll advance on forward. Then after our loop breaks, we'll set on.next to a new node. that is, the node being added to the tail. We've written our code, so let's see the add to tail method in action. You probably noticed that every time we run this, we have to touch every node in our list before adding a new one to the end. That's where the big O, or time complexity, comes in. It's a measure of the efficiency of our add to tail method. Let's just pretend that each time our loop runs, it takes a full second. If n is the number of nodes in our list, add to tail will take n seconds to complete. This makes our time complexity O of n, or equal to the number of nodes in our list. In technical terms, it scales linearly with our input. Moving on, let's retrieve a value using an index. We'll start with a pre-built list. Unlike an array, we can't use direct indexing to retrieve a node. By using the same onPointer method again, and decrementing our index every time we advance, we can count down until finding the node we want. Once that happens, we just return the value of that node. With this method, we do have an edge case though. Namely, what if we try to get an index that is out of the range of our list? We'll go effectively off the end and have to return some value like none or false. Our method will take the target index as the argument. Then, our while loop will have to check for either the end of the list or index reaching 0, our terminal conditions. Within the loop, we of course are going to want to advance or on and decrement the index, as we talked about. Depending on the final outcome of the loop, we're then going to use an if statement to either return the value or false. Now let's watch this in action next to the code. Okay, what's our big O this time? With big O, we're pessimistic, meaning we assume the worst case. Here, the worst case is, of course, falling off the end of our list. When that happens, we traverse the whole list without finding our index. Like last time, when we touch each node exactly once, we're running an O of n. There's a couple different ways we can implement delete. First, we could delete at an index. On the other hand, we could delete all nodes that match a specific value. Let's assume we do want to delete by value, and there could be multiple of the same value. We can infer that by pointing around a node, it's no longer connected to our list. In effect, this deletes our node, because there's no more reference to it. If we want to delete the last node, we simply set the second to last to null. We'll set up our onPointer like normal, except this time we'll have to look to on.next to see if it's a candidate for deletion. If that's the case, then we'll change our pointer in on to on.next.next, or 2 ahead. In other words, we set on.next to on.next.next. It's like that node never existed. Now we just move forward our onPointer and continue as normal. When deleting the last node, we have to be careful not to go off the end on accident. Here's our code. We take, of course, the value slated for deletion as an argument. We set our onPointer, just as we always do. And in the loop, we check both on and on.next to make sure we don't go off the end accidentally. In the loop, we look 1 ahead to see if we can delete that value. If so, we set on.next to on.next.next to point around that node. Finally, we advance our onPointer, and that's it. We're done. Let's see this one run side by side with the code. And the time complexity for this one, well, it's pretty straightforward. We're going to have to check each node at least once to make sure we see all the values. That means linear time, best and worst case. All right, guys, you now know all about linked lists and their common methods. That should give you a really good start for solving linked list algorithms. If this video gets enough likes, I'll be motivated to do a linked list algorithms video as well. So definitely let me know if you want that. Otherwise, I'll be releasing the next video in this series soon, and I hope you found it helpful. And again, don't forget to like and subscribe so more people can see the video. Anyway, I will catch you guys soon.